Hi folks, so we're going to build off of what we did on the last video using a much more complex buffer. So if you notice here, we have a buffer that we're trying to prepare that is 450 milliliters, 50 millimolar tris pH 8.2, 150 millimolar sodium chloride, 3 millimolar PMSF, which is a protease inhibitor to keep proteins intact in a buffer, and then 5 millimolar beta mercaptoethanol, which prevents disulfide bonds from forming, or at least undoes it when they do. So it keeps proteins nice and flexible and similar to what they would exhibit inside of a cell. And so these components are a complex buffer that you might see very commonly in a biochemistry lab. So we here have to show some calculations. I've given you some handy information here about the components in our buffer, just some basic pKa molecular weights, also the phase you find these in. And one thing I want to point out here is that anytime you see something that's a solid, you always want to get it into grams because obviously that's how we measure solids. We want to convert all of our things into grams. If it's solutions or liquids, we want to get those into a volume unit. We can handle, of course, like a volume. Now you can also do liquids in grams as long as you know the density, but we'll just kind of go with the rule of thumb that anything that's in a liquid form or a solution form should be solved into milliliters. Okay? So let's start out here. We want to make 450 mils of 50 millimolar tris pH 8.2. And anytime you see something like that where you see a pH and then it's a buffer, you know it's a buffer because it has a pH explicitly given. And it has a buffering capacity given the concentration of the buffer. We need to start solving the Henderson-Hasselbalch equation like we did in the last video. And so what we can start out with, of course, is our lovely equation. Henderson-Hasselbalch is pH equals pKa plus the log of A over HA. Now, of course, I like to do a little bit of intuition before I start this. Looking here at tris, the acid form has a pKa of 8.1. We are above the pKa. Our pH is above the pKa, I might want to say. And therefore, we need more A than HA. And I think about this kind of like a line. If our pKa is 8.1, low pHs have more acid, high pHs have more base, and we happen to be right here at 8.2, and so we'll be slightly favoring our A over our HA in our buffer. Of course, this is a valid buffer. It's within 1 pH unit of the pKa, and so we have a very good capacity to have a well-buffered solution here. So one thing I like to say here, again, is use my intuition and say we should have more A than HA because our pH of the buffer is above the pKa value. And we'll check that in a little bit and make sure all of our numbers are coming out right. Alright, so I'm going to start plugging in some values. We know our pH we want is 8.2. Our pKa is 8.1. And we don't know this part, and we're trying to solve that. Okay, I'm going to subtract 8.1 from both sides. 0.1 is equal to the log of A over HA. Okay. I'm doing a common log. We do 10 raised to both sides. 10 to the 0.1 is unsurprisingly 10 to the 0.1 is 1.2589. I like to not round as much as possible here because when these are logs and ratios, any rounding can throw us off early on. So I like to try to go out to 4 decimal places or so to start. And that's going to be our ratio of A to HA. Does that match what we said before? Yeah, we have 1.25 A's for every 1 HA. So we have more A's than HA like our intuition told us earlier. Cool. So let's talk about how to solve it. Again, we're going to set our buffering capacity equal to A over A plus HA, and then we're going to use this ratio to do two equations to unknowns. So again, 1.2589 is equal to A over HA, slightly favoring the A, and our buffering capacity is 50 millimolar, equals A plus HA. Remember, the capacity of a buffer is given by the ability to either soak up H's or OH's. And so this A and HA is the total capacity of the buffer, 50 millimolar concentration. So again, I like to multiply by HA on both sides of this of the ratio equation. So our A is equal to 1.2589 HAs. And then I'm going to plug that in here for A. 50 millimolar is equal to 1.2589 HA plus HA. So 50 millimolar is going to be 2.2589 HA. Cool. And then we want to solve for HA. We'll divide both sides by 2.2589. We end up with HA equaling 22.1347 millimolar. And then remember, if we know HA, we also can figure out A. And so 50 minus that is going to be our A minus. 50 minus 22.1347 is 27.8653 millimolar. Great. Again, we have more A than HA, and that's why I do that intuition step at the beginning, because if you messed up anywhere in this process, and these get backwards, you can catch yourself, and you don't make a buffer that's wrong. So that's that. So we have more A's than HAs. Okay? Now to get our concentrations, we're going to want to start plugging in our concentrations. I'm going to start with HA, which is our tris HCl. Okay? And our tris HCl, we know, had a molecular weight of 157.6. That was given on the first slide. And that's all it is. And that's grams per mole, of course, because it's a molecular weight. And we said that its concentration was 22.1347 millimolar. So let's start converting that. Let's get that into moles. We want to get rid of our millimolar. Put it into molar so we can use our mole unit up here. So 22.1347 times, or divided by 1,000, is 0.02213 molar. Okay, and I'm going to take that, and I remember molar units are moles per liter. Okay, so now we can start using some of our obvious things. I'm going to use the molar mass because it's given here. So that's going to give us 157.6 grams per mole. If we do it that way, then our moles will cancel. We'll be in grams per liter. Remember, this is a solid, so we want to end up only in grams. How do we cancel our liters? We use our volume of the buffer in liters. We had 450 milliliters, which is 0.450 liters, just dividing by 1,000. And that should give us our grams as our unit. Okay, so I'm 157.6 times 0.450. We get 1.5698 grams. Our balances can go out to 4 decimal places. So that is how much tris HCl we're going to need. I'm going to write that down here on a piece of paper so I don't forget. Alright, so that's A, HA. Let's do A now. So again, we wanted our A concentration to be 50 minus 22.1347. And that was a concentration of 27.8653 millimolar. Okay, so our A minus was 27.8653 millimolar, is equal to our trisma base. Cool. So we got that much. Let's start out, and we know our molecular weight from that sheet was 121.14 grams per mole. So we end up with 27.8653 millimolar. 1 molar over 1,000 millimolar. So we can get this into moles. And that's going to give us 0.0278653 molar. moles per liter. Okay, again, we want to get rid of our moles, so I'm going to divide by, or multiply by our molar mass, 121.14 grams per mole. Moles will cancel. We're in grams per liter, times 0.45 liters. Oops, fix that. Okay, let's check that out. Times 121.14 times 0.450. I get 1.519 grams of trisma base. So now, if you notice, from the last one, we had 1.5698 grams of tris HCl, but we have fewer grams of trisma base. And didn't I say early on that we would have more of the base than the acid here? Well, don't try to compare grams to grams, because remember, the molar masses are different, and so that's going to throw us off. These trisma bases weigh less. They weigh less by an HCl. And so we want to be sure that we are not comparing grams to grams, because that doesn't matter, but moles to moles, because those are comparable quantities, whereas grams are completely incomparable due to the differences in molar masses. Okay, cool. All right, so let's look at some of what our buffer we had earlier. We had our different components in our buffer. We had to make a 450 mils of tris. Check. All done. We knew we have to get 1.5698 grams of tris HCl and 1.519 grams of trisma base. So let's work on the other ones. Let's do 150 millimolar NaCl. Okay, let's jit this into molar like we did before. It's all downhill from here, folks. It's going to be much easier from here. That's going to be moles per liter. Okay, and that's going to be millimoles per liter. Okay, so that's going to give us moles per liter. 150 divided by 1,000 is 0.150 moles per liter. Our millimoles per liter will cancel. Cool. Okay, what are we going to do? Well, we're going to do the same thing. We're going to multiply by the molar mass and by our liters of buffer, 0.450 liters. 0.15 times 58.44 is 0.45. So we would weigh out 3.9447 grams of NaCl in this buffer. Okay, so we've been to the scale 3 times now. We've weighed out NaCl, we've weighed out tris HCl, and we've weighed out trisma base. But now we are done, because the other two components of our buffer are PMSF and beta-mercaptoethanol. PMSF is a 0.1 molar solution. It's already dissolved in water. And our beta-mercaptoethanol is a pure liquid. And so from now on, we're going to be trying to get to milliliters on this. Okay. So our NaCl, all of our solids are all done now. So let's work on our PMSF. Okay, so we need to make a 3 millimolar PMSF, and our stock of PMSF is at 0.1 molar. Okay, so all we're going to be doing is diluting our stock, which is already a solution, down to a concentration. And remember, for dilutions, you might use this equation. C1V1 equals C2V2, or if you like M's, M1V1 equals M2V2. I like M's. My name's Mauser, so it's easy for me to enjoy the M. If your name is C or you like C's more, go ahead and use that one. It really doesn't matter. They're the same thing. A couple things to remember is M1V1 is our stock. That's where we're starting. M2V2 is where our final solution. So, a couple things we know is our 3 millimolar PMSF is what we're trying to get to. So that is going to be our M2. Our V2 is our volume of buffer, 0.450 liters, or 450 mils, whichever one you like. And then our stock is going to be our M1. And so what we're solving for here is V1. We need to know how much of our stock we need to dilute to 450 mils to end at 3 millimolar. So I'm going to set this up. We have 0.1 molar, V1 equals 3 millimolar times let's do milliliters because that's an easier unit to work on. 450. And again, this equation works perfectly no matter what unit you use, but it has to have the same unit. If we try to do 3.1 without changing the unit, something's going to get messy. And so we always want to make sure our units are the same. And so here I think I'm going to just get the molar to millimolar by multiplying by 1,000. So again, remember 0.1 molar is 100 millimolar, V1 times 1,000, right? Equals 3 millimolar times 450. So if I solve this guy, 3 times 450 is going to be 1350 equals 100 V1. So that means our V1 coming out of that, divide by 100, 1350 divided by 100, it's 13.5, correct? Yeah. 3 mils times 450 mils, 3 millimolar, 450 divided by 100 is 13.5 milliliters for our buffer. Okay, because we want quite a bit of this, we have to use about a 1 to 100 dilution, or a little bit more than that. So we're going to end up with 13.5 mils of PMSF in our buffer. Okay, so that's one, and we have one more to go. The last thing we want to do is to put in our beta mercaptoethanol. So let's look at our buffer recipe. 3 millimolar PMSF. We just did that one. We have our solutions. So what are we going to do here for our beta mercaptoethanol? Remember, this is a liquid. It's a pure liquid, not a solution, so we can't use M1V1. So we're going to have to use a different solution here. We're going to have to use a basic calculation just like we did before, but we're going to want to end in milliliters. So let's take our 5 millimolar. Again, let's convert that to molar. Okay. Millimolars will cancel. It's going to end up with 0.005 molar, or moles per liter. Same thing. And let's do the same thing we did earlier. Now, if you remember, molar weight for this was 78.13 grams per mole. So let's try that out. .13 grams per mole. That's going to cancel moles. We're going to make grams per liter. Again, we're going to get rid of liters by multiplying by our buffer volume. And we want to stop here in grams. Nope, we're in a liquid, so we want to end in mils. And the last piece of information given on that first page was the density is equal to 1.1 grams per mil. So I want to get rid of grams, put 1.1 on the bottom, and we'll end with mils on the top. So what do we get here? 0.005 times 78.13, that's 0.45 divided by 1.1. We end up with 0.1598, what unit here? Milliliters. So that's where we ended here. Now, I might like to put that into a volume I like, which is microliters, and I'm just going to divide that by 1,000. Oops, I'm going to multiply by 1,000. Sorry, that's my bad. Oh, crap. Oh, well. Times 1,000 to get to microliters. So 159.8 microliters. Okay, so we have solved all of the components of this very complex buffer. And so let's talk about how we're actually going to make this buffer. So our buffer, recall, is a complex buffer. we have multiple components in our buffer. We need to weigh out tris. We need to weigh out 1.5698 grams of HCl and 1.5190 grams of trisma base. That's going to give us our buffered piece. That's the first part of our buffer. We solved that using the Henderson-Hasselbalch equation and molecular weights. All right, NaCl, we're then going to go back to the scale and weigh out 3.9447 grams of NaCl. We're going to add that to the dry powders we weighed out before in the same beaker. Remember, we're trying to use a beaker that has a final volume of 450 mils, so you need a large beaker, like maybe a 1 liter or a 500 mil. Put those dry powders together. Then we're going to squirt a little bit of our PMSF. We're going to add 13.5 milliliters of 0.1 molar PMSF to the dry powders. They'll soak right in. And then we're going to add 159.8 microliters of beta-mercaptoethanol straight to those dry powders. It was a little bit wet because of this, but we have a little bit of liquid onto that dry powder. Are we done? Nope. Then all we need to do is add water to get to 450 milliliters. Give it a quick stir, shake, let everything dissolve, and check your pH, and you should be good to go. So that is how you would make a complex buffer. Again, we're going to do each piece independently, add them all together, and then just add water, and it's a miracle. You end up with a very nice buffer. Hope that helps.